In your chemistry class, your chemistry teacher might have told you that the only way to balance chemical equations is to use trial and error. And in this video, I want to debunk that theory and in fact show you a more elegant way to derive the coefficients in a chemical reaction. Alright, so let's consider this chemical reaction. SnO2 plus hydrogen, that makes tin plus H2O, water. And our goal is to balance this. Well, how do we balance this though? Well, you can basically use trial and error in this problem right now, because this is not a very advanced chemical reaction. In fact, there's only 2 reactants and 2 products, which aren't that all complex. However, what I want to do in this video is to balance chemical reactions using linear algebra. Let's notice that we can use a system of simultaneous equations in order to solve this problem. Alright, so first of all, let's put some coefficients in front. So X SnO2 plus YH2 makes ZSN plus WH2O. Alright, we basically put these coefficients in front to indicate that they are the coefficients for the chemical reaction, and we're interested in solving for them in order to balance the chemical equation. And now this is not enough. We need to propose a condition in which these coefficients satisfy, or else we're basically doing like a trivial empty step over here. Now, notice that for Sn, we want x to be equal to z, right? Because x and z are both in charge of the amount of SNs. So x is equal to z. For oxygen, we want 2x, because there's a subscript 2 over here, to be equal to, let's see, W is in charge of 1 oxygen, so 2x is equal to W. For hydrogen, we want 2y to be equal to, well, over here, 2w. So, putting the variables to one side, what we have is x minus z is equal to 0. 2x minus w is equal to 0. And 2y minus 2w is equal to 0, which is equivalent to saying that y minus w is equal to 0, dividing 2 on both sides. Alright, so after this, we can set up a system of equations. So the system of equations we will need are over here. And let's construct a matrix. The matrix is as follows. 1, 0, minus 1, 0, 2, 0, 0, minus 1, and 0, 1, 0, minus 1. And the constants are all zeros. And let me just put that in a different color to make this look more vibrant. And notice these rows are correspondent to what we have over here. The tin, the oxygen, and the hydrogen. Now the goal in this video is to basically solve for these coefficients, right? And so why not put this in a reduced row echelon form? We do this by elimination. So, eliminating this matrix, we can have, well, first of all, let's subtract 2 times row 1 from row 2. So, we'll copy row 1, and row 2 becomes 0, 0, 2. Is that right? Yep. And minus 1. And we can copy the third row out front. And the constants stay the same. And what I'm going to do in this next step is to basically swap row 2 and row 3. And by doing so, what we have is this. Okay, fantastic. Actually, we already derived an expression and a condition to get x, y, z, and w. So let's see. From here, we know that 2z minus W is equal to 0, which is equivalent to saying 2Z is equal to W. And over here, what we have is Y minus W is equal to 0, which is equivalent to saying that Y is equal to W. And over here, what we have is X minus Y is equal to 0. But we also know that this means X equals to Y, but Y is equal to W. So in total, what we have as a net equation is X is equal to W. All right, and let me just put this in a further format. So Z is equal to W over 2. So now every of the coefficients are in terms of W. So this means W is our free variable, which means that we can basically pick any value for W, and each of these coefficients are going to depend on what we choose for the value of W. All right, so I think a convenient choice is W is equal to 2, which yields Z is equal to 1, Y is equal to, let's see, 2, and X is equal to 2. Oh, I'm really sorry about this. This should be 2x. And so 2x is equal to y equals to w. And so 2x is equal to w, which means that x is equal to w over 2. All right. So this means that x is equal to 1. Okay. We have all the values for our coefficients, and we can basically plug them in. And therefore, our previous chemical equation, let's duplicate this and put this over here. This is actually SnO2 plus 2H2, which makes 1 Sn, which is Sn itself, plus 2H2O. And that's it. Well, using trial and error, you can also solve this, but what I want to show you is basically how simple this is. This is an algorithm, and basically by setting up a bit of simultaneous equations, you directly get the balanced chemical equation. And because I'm doing this by hand, this might take a bit of time. So if you put every one of these steps into a computer, so about putting these coefficient variables out front, about converting this to a matrix system of equations, and converting this matrix into row echelon form, your computer can do this very fast. And in no time, if you plug in this chemical equation, it will just generate the answer for all of the coefficients in front of the reactants and products. And this is really powerful because this means that we can basically generate the coefficients in front of all the substances in a very complex chemical reaction using a computer. And this is really beneficial because this means that balancing chemical reactions, which basically is the conservation of the law of mass, which is really important in physics and chemistry and all of daily life. It's similar to the conservation of energy, which cannot be violated. This means we can derive these balanced chemical reactions very quickly. Alright, thank you for watching this video, and I wish to see you again.